is now, instead of labeling this as lecture 1, and the second column is lecture 2, which obviously didn't work out quite well. They're now just labeled by sections. What we did last time is we got to about here. So we talked about the motivation for WIMPs, the WIMP miracle, the discrete WIMP miracle, and then it started off on WIMPs and supersymmetry. And so I had a chance to introduce supersymmetry very, very quickly to you. And we were in the middle of talking about the stability and the lightest supersymmetric particle, which we found out that basically proton decay and other things like electroweak precision measurements sort of suggested there was a discrete symmetry which made the lightest supersymmetric particle stable. And we were in the business of finding out which particle that actually was. Okay, so that's where we are right now. Just a note, as you see, we didn't get through all of lecture 1 material. I am quite sure we won't get through all of this material today, but rather than try to speed up and perhaps suppress questions, which would be absolutely the wrong thing to do, I'll move along at a reasonable pace, but kind of continue on. And if we don't get through all this today, that's fine. Tomorrow, there's another session which we will use to get through all the rest of this, and at the same time, reserve some time for questions. Okay, so that's the plan. So the basic message is, please do keep the questions coming because they're fantastic. And especially given that I'm not with you, it's important that we take time for those. Okay, so we were, as I say, in the middle of WIMPs and supersymmetry. I had just started telling you about super partners, and we had some nice questions about the superparticle spectrum, and mentioned that it has an approach to the gauge hierarchy problem that has been quite influential. And here we had just the very last comment, which again, I want to sort of emphasize is sort of an interesting fact. I'm not sure if I know all the latest details on this, but the bottom line is it's not at all clear to me that if you have a greater than TeV stable particle, it has to be neutral. And so I think that actually might be an interesting fact, given that, for example, the bounds on a lot of these things are over TeV anyway. Thinking of them as being multi-TeV is not much of a stretch. And could it be that there's actually a stable, say, gluino, which is floating around in the universe? Anyway, I leave that as an open question. What we will do now is assume that, in fact, the standard assumption, which is that everything that's stable in the cosmological scales has to actually be neutral. And therefore, we will now want to figure out what possible supersymmetric particles could be this neutral dark matter candidate. Okay, so here is a table where I've listed various neutral standard model particles according to their spin, okay? And so you know what they are. There's these gauge bosons, the B and the W naught, which combine to form the photon and the Z. There's Higgs in the standard model, which I'll call down type for reasons we won't get into. There's neutrinos, which are of course neutral. And then, we know there'd be a particle called the graviton. Maybe it's not part of the standard model, but it exists. So in supersymmetry, then what happens? Well, we supplement this with a bunch of new particles. First thing is that we have to introduce another Higgs. So I mentioned this last time, that supersymmetry is more than just a doubling. And so here we go, we have another kind of Higgs, which I'll call up type. But then after that, all we need to do is double by adding fermions for bosons and bosons for fermions. And so what we do was we have this BiNo, which is a spin 1/2 fermion partner of the B boson, the WiNo, which is the same thing but for SU2. Then we have Higgsinos, which are fermion partners of these scalar Higgses down here. Then we have a neutrino, which, as we discussed last time, is actually a spin 0 partner of the neutrino. And of course, there's one for every flavor. And then there's a partner to the graviton, which is called a gravitino. Most important for this lecture is that these 4 things, because they're all spin 1/2 fermions, they actually mix. And the mixing is very interesting. It can be understood in terms of the parameters of the theory, which are listed up here. But basically what we need to know for now is that these four mix into mass eigenstates, which are called neutralinos, which have typically this notation: chi1, chi2, chi3, chi4, and chi1 is the lightest. Okay, but they're actually just various components. Each one of these has various components of each of these four down here. Now, I won't get into this in much more detail because there's no time, but this neutrino, it turns out, is fine in terms of being electrically neutral, but it has a lot of problems as a dark matter candidate simply because of experimental constraints. It basically interacts too strongly, and for reasonable masses and minimal models is ruled out. It's been sort of, let's say, it was searched for in the 90s and people didn't find it, so that's gone. Okay, so sort of 0th order approximation, this is not a good dark matter candidate. The gravitino is a good dark matter candidate, and in fact, it was the first supersymmetric particle which was thought about as a dark matter candidate by Pagels and Premack in 1982 or so. But we'll come back to that. And the neutralinos, or this particular lightest one, are really sort of the main WIMP dark matter candidate from supersymmetry. And so we'll sort of explore that. Okay, but now you can say, well, you know, you found out that it's electrically neutral, but is it the lightest one? You've dumped a whole bunch of degrees of freedom into your theory. Only the lightest one is possibly dark matter. And so, you know, we should approach this from the other point of view, namely, give me a model and I will calculate the masses and figure out which one is the lightest one. If it turns out to be a neutralino, great, but maybe it turns out to be, you know, a left-handed upsquark, in which case, well, not so great, right? So what we'd have to do now is think about how masses and couplings and parameters are determined in supersymmetry. And this is an absolutely beautiful topic and is sort of, if you understand some of this, why people were excited about supersymmetry for so long, and many still are for good reason. Supersymmetry, because it kind of softens all sorts of infinities, is a theory that can sort of exist up to very high scales, like the Gut scale, as I'll define, or the Planck scale. And this is how it's connected to string theory, which is, you know, sort of, you can think of as a theory of Planck scale physics. It patches onto that because we can sort of start at the top scale and connect it to the weak scale theory, or start at the weak scale and go up to the Planck scale theory. And we do that by relating things to renormalization group equations, or renormalization group evolution. Okay, so I'm sure you're all familiar with this idea. Gauge couplings, of course, renormalize group, normalization group evolve. And why is that? Well, if you're changing the momentum transfer scale, it's equivalent to changing the length scale. And even in sort of classical E&M, we know that charges have different values depending on how far you are from them if they're in a dielectric, right? So here's a picture of a charge here, and then here's a dielectric with little plus minus, you know, dipoles that can kind of pivot around. And, you know, depending on how close this particle gets to here, it will experience different amounts of repulsion because of this dielectric sort of modifying the effective charge of this thing if they're in a dielectric. And in quantum field theory, putting anything in a vacuum is putting it in a dielectric, because we know quantum effects basically allow you to sort of pop particles out of the vacuum for short times. And so this is at least a heuristic way of understanding this. Charges, their values, their gauge couplings, for example, depend on the momentum scale you probe them at, the length scale you probe them at. Extremely famous example is, of course, QCD, where we have asymptotic freedom. Here's the momentum scale, and this is the strong coupling. And, you know, this change, this normalization group evolution of alpha sub s, has been measured with great precision for a whole bunch of different mass scales. And you see that, you know, they change, and of course they go off to zero at very high momentum, which is the statement of asymptotic freedom. Okay, so that's what happens just in the standard model. What about in supersymmetry? Well, in supersymmetry, same thing happens. Every single parameter of the theory renormalization group evolves. And we could, for example, start with the gauge couplings I just talked about. Now, one seemingly completely different fact from supersymmetry is grand unification. Okay, so we know that in the standard model, we have a bunch of particles. They matter particles. They have funny quantum numbers. We have a left-handed doublet, and we have one left-handed singlet. Then we have, quarks with hypercharge 1/3, 4/3, minus 2/3. On the face of it, this looks like rather bizarre numbers, and of course they're very precisely known from experiment. But you could ask the question, why? Why do we have these numbers? And one beautiful observation stemming from Howard Georgi in the early 80s and others is that these can be grouped into multiplets of higher symmetry groups. So instead of the standard models SU3 cross SU2 cross U1, you can consider a grand unified group, SU5, which has multiplets like the vector multiplet 5 and 5 bar and 10, etc. And you can put all of the standard model particles beautifully into these multiplets. And you can only do that because these have exactly the hypercharges they have. If this upper right was not 4/3, but 1 or minus 2/3 or something, that doesn't work at all. And so the fact that this bunch of seemingly random representations fits beautifully into these two is quite interesting. And even more interesting maybe is that if you go to an even larger group like SO10, these 5 bars and 10s fit into a 10 or 16 of SO10. And these are these spinorial representations where you have just plus and minus under 5 charges. But basically they fill out all of the 16, except with one remaining one, which turns out to have the quantum numbers of a sterile neutrino. So basically, this is extremely suggestive that there is grand unification in nature. And in the SO10 case, it's perfectly beautifully aligned with the idea of neutrino masses, because you actually need another particle, which is the quantum numbers, to be the sterile neutrino. And so even though we kind of don't include that in our standard model, most of us probably think that there are such things, and they kind of hang around just completely on their own, but in SO10, they're unified in with all the other particles. That's an absolutely beautiful fact. And for me at least, this is one of the most convincing reasons to think that there is some higher order, some higher symmetry to particle physics. Okay, any questions? Okay, did I see one? Yes.
So if SO10 is such a successful group to do grand unification, why haven't we said, okay, look, we found this great solution, we're done? Like, why are people continuing to look when we have something that looks so nice?
Well, so the thing is that, of course, not all of these particles are, for example, mass degenerate, which would be the prediction of a pure SO10 theory. So they're all broken into pieces, just as the gauge group SO10 is broken into SU3 cross SU2 cross U1. And so you need some further evidence that this grand unification happens, right? And so there are extra particles that are predicted in SO10 that you could look for. We haven't found any of those yet. There are a bunch of interesting predictions. I won't mention too much, but proton decay actually is reintroduced with this sort of grand unification. So if we found proton decay, all of a sudden that would be extremely strong supporting evidence for grand unification, but we haven't seen that yet either. So, it's still at the level of, experimental verification, a speculative theory, but I'm just, every time I come back to this, I'm continually amazed how this has worked out. And, there's one of these ideas that really should be right. Okay, maybe it's not, but it really should be.
Thank you.
Okay.
Yeah. I saw you mentioned the gravitino. How these higher order symmetries include the gravitino in the theory? Because I know that there are some problems with the graviton in the contributed theory.
Okay, so I think you were asking about the gravitino. So the gravitino is sort of sitting on the side of all this. So you can kind of think of, just to make sure we're clear, we have, the standard model, and we can extend it in two ways. We can supersymmetrize it, kind of think of that as going up, or you can grand unify it, which is going this way. And what we're really interested in is doing both supersymmetry and grand unification. I'll talk about in a second. But the gravitino comes not from the grand unification, but it comes from supersymmetrizing, right? And so all these theories include a gravitino in them once they're supersymmetrized, and the gravitino doesn't unify in with any of these things. It just, it unifies by supersymmetry with the graviton, but it doesn't unify by any grand unification theory with any matter multiplets. And we'll talk about gravitinos in the context of dark matter later in this talk series, probably tomorrow. It has some extremely interesting implications, but let me not get into that right now. Okay.
More? Yeah, I think we're done. So let's keep
Okay.
going, Jonathan.
Okay, very good. Now, as we just discussed, we think this is a beautiful idea, at least I do, I think you should. We don't have hard particle physics evidence, sort of having discovered a grand unified theory particle, but we have some other very interesting evidence about it, and that's in this slide. So this coupling constant mutation. If you really think that all of our three different gauge groups are unified into one, then all the couplings ought to be unified into a grand unified coupling. And you say, well, yeah, great. Obviously they aren't, because they're very different. The strong coupling is bigger than the weak coupling is bigger than the electromagnetic or hypercharged coupling. That's true, but now connect this to grand renormalization group. They don't have to be unified now, right now, at our energies. They can be unified at some higher energy scale. They change. And in fact, this is what you would expect, because the grand unification is clearly broken at some point. So they're kind of unified at some high energy scale. Then when the unification is broken, then the couplings will go their own way. But we should see evidence of that, sort of vestigial evidence of this unification, because if we run the couplings up to high scales, then they ought to meet if there's any merit to this grand unification idea. Now in the standard model, what I just wrote, with the standard model particle content, these renormalization group equations are very well defined, and they the way you do this is you start at the weak scale with whatever values you have for the three different couplings, alpha 1, alpha 2, alpha 3.